All right, so the next thing that we're going to add is talking about a couple of ways that we can form magnetic fields. And so the thing that we want to emphasize right up front is that magnetic fields are caused by currents. So we're going to focus on two different ways that current carrying wires will create a magnetic field. So the first of those ways is if we have a long straight wire. The second one's going to be if we have a current loop. So a long straight wire is exactly what it sounds like. It's nice and long and straight. Current loop is exactly what it sounds like. It's just a circular loop that the current circles around. So one of the things to emphasize, because again we're going to have a right-hand rule here, is that the long straight wire, our current will be straight and the magnetic field circles around it. In our current loop, we're flipping that around. So we've got the current that's circling, and that'll end up having a straight magnetic field through the center of the loop. So we're going to see that for the two magnetic field cases that we're going to consider, there's going to be a straight piece and a circular piece. So in the case of the long straight wire, it's the current that's traveling along a straight line. The magnetic field circles around it. In the case of the current loop, it's the current that's circling around, and we've got a long straight magnetic field through the center. The other thing that we need to go ahead and do here is there's going to be a new constant, universal constant, that we're going to introduce. So up until now, we've seen this one, epsilon naught, right, 8.85 times 10 to the minus 12 coulomb squared per Newton meter squared. This is called the permittivity constant. It's also known as the electric constant. Well, what we're going to add is a new one, mu naught. It's 4 pi times 10 to the minus 7 Tesla meters per amp. This is called the permeability constant, and it's also known as the magnetic constant. So in the same way that epsilon naught, or as the way that we often dealt with it, right, we knew how epsilon naught related to K, our Coulomb's constant. But in one form or another, epsilon naught was in most anything we did with electrical stuff. Mu naught is going to keep popping up in our magnetic stuff. So let's consider our long straight wire first. So here's a long straight current wire, but notice the way it's oriented. So the dot tells me that I've got a current that's coming out of the page. So basically this is a long straight wire that runs in and out of the computer screen here, where the current is flowing out towards us. And I'm going to be interested in the magnetic field at a point P. Well, the magnetic field due to a long straight current carrying wire at a point P is given by mu naught I divided by 2 pi little r, and this little r is the perpendicular distance from the wire to point P. So in this case, there's our little r, right? So here's the wire, here's point P. Now, we'll learn a right-hand rule to help us figure out directions, but without worrying too much about directions at the moment, what we're going to see is that, again, at this particular choice of point P, the magnetic field will point up. So one of the things that we will emphasize is that the magnetic field will lie on the line perpendicular to the line that connects point P to the wire. So here's the line connecting point P to the wire, which means this is the line perpendicular to that the magnetic field vector has to lie on. And so in this particular case, it happens to point up. And if you don't understand where that's coming from right now, don't worry about it. It's a right-hand rule, and we'll talk about it in class. If I pick a different point P, so here's a second point P. Well, again, here's the line that connects point P to the wire, which means the magnetic field has to lie on a line that's perpendicular to that, and sure enough, the magnetic field at this point P2 points to the left. We can keep going around, so here's P3. Again, here's the line connecting P3 to my wire, so the magnetic field at P3 has to point up or down. In this case, it happens to point down. At P4, again, here's the line connecting P4 to the wire, so the magnetic field at P4 has to point perpendicular to up and down, so it's got to point left or right. And so part of what you notice here is that if we keep filling in more and more and more points, what you see is that the magnetic field circles around the wire. So this was the statement that I made on the very first slide of saying that we're going to have a straight piece and a circular piece for both of these magnetic fields due to current carrying wires. In this case, our current is the long straight piece, and the magnetic field circles around our long straight wire. There will be a right-hand rule, and again, we'll go over this in class, but here's a picture sort of representing the right-hand rule that says if you put the thumb of your right hand in the direction of the current, so if you sort of stop where you are right now and hold up your right hand so that your thumb points straight back towards you, you'll notice that your fingers are curling around in exactly the direction that the magnetic field goes around. So this is one of the right-hand rules that we'll add to our toolkit in terms of figuring out the directions when we're dealing with magnetic stuff. So our other magnetic field due to a current carrying wire was for a circular loop. So here's a situation where now it's the current that goes around in a circle, and I'm going to be interested in the magnetic field at point P in the middle of the circle. So this is going to be the magnetic field due to a current carrying loop of wire at the point P that's located at the center of the loop. And again, I've got an expression here that tells me that the magnitude of that magnetic field is going to be equal to, here's my magnetic constant mu naught, times the current going around my loop, over here 2 times r. So one of the things you'll notice is this expression is very similar to the other one. What's different here is that instead of 2 pi r on the bottom, this one just has 2r. And the r here I've left as a big R because it's actually the radius of our circular loop. So in this case, here's big R. It's the radius of the loop because we're interested in point P sitting at the center. So again, we'll have a right-hand rule that'll tell us if your current curves around, in this case counterclockwise, then the magnetic field will point out towards us. So again, here's the magnetic field pointing out towards us. That's what this dot is helping to represent. And so in this case, I've got a straight magnetic field, right? The magnetic field points straight through the center of my circular loop. So now it's the current that's circling around, and the magnetic field is the straight part. Now, that means, or sort of the larger picture for this, is that for any circular loop of wire, this is what the magnetic field looks like. So here's the current that's moving to the right in the front and around and to the left in the back of this circular loop. And here's the magnetic field that's caused by this circular loop of wire. And one thing to point out is this magnetic field looks very, very similar to the magnetic field that's caused by a bar magnet. So one of the things that we'll emphasize is that magnetic loops, or current loops, act like bar magnets. They'd line up the same way bar magnets line up, right? So if you put a bar magnet into a magnetic field, it's going to line up with that magnetic field. The same thing's true for your current loop. If you put a current loop into a magnetic field, it will line up with the magnetic field. So these are the two sort of special cases that we're gonna deal with. But what this does is it gives us a way to put together long straight wires and loops of wires so that we can drive currents through them and figure out what the magnetic field is at certain points given the configuration of wires that we've got.